Okay, hi Zach, welcome to lesson 114, and we're on page 479, and we are almost done with this whole book. And today's lesson is going to be fun because we're going to be able to use a graphing calculator for the first time. We're going to talk about exponential growth, exponential keys, and then how to use a graphing calculator to figure out those problems. Okay, so this is going to be fun, and hopefully you have your graphing calculator. It came by Amazon for this lesson, hopefully. We'll see. All right, I have a few jokes about unemployed people, but it doesn't matter. None of them work. Okay, let's jump right in. Okay, the exponential key. This is a key that is used on your graphing calculator, and this is how it's going to work. The calculator is an easy way to do exponents. So remember, the exponents look like this guy, 3 raised to the 7th. And you're probably like, why do I need a calculator to help me figure that out? That's not so hard. I can figure that out myself. But you're going to see that sometimes the problems look more like this, or look at this exponent. Like, how would you do that? I mean, that's harder, right? So they definitely increase in complexity. So learn to do these first by using your graphing calculator, and then it'll be easier to do the more complicated ones, okay? So if you have a scientific calculator right now, and you can probably use the one on your phone, and if you turn the phone to its side, it will give you more keys or more functions to be able to do these. So on a scientific calculator, it's going to either look like this, like y to the x, or it's going to have this little symbol, okay? And this is usually what it looks like on a graphing calculator. Okay, so let's just start doing these and see if you can figure it out. Okay, so let's see, we're going to do 2 to the, okay, let's try one, 2 to the 5th. Now, we already know, you're probably already going to know this, that when you figure this out, the answer is going to be 32. But we want to start with an easy one, so that way you can make sure that you're doing it right on your scientific calculator or on your graphing calculator. Okay, so here's how you do it. Step 1. And remember that the problem is this, 2 raised to the 5th exponent. So if you have a scientific calculator, this is probably what it has on your phone. You push the number 2 first. Okay, this is what the display is going to show you. Then you press the y to the x. Okay, the display is still going to be showing you that 2. And then you do the 5. Because remember, the problem is, I'm going to write it here so we can see it on the same 2 to the 5th. Okay, so you push a 2, this is what the display shows. You push y to the x, the display still shows this. Then you push your 5, and then you hit equal. And if you did it correctly, you should get the number 32 for your answer. Okay, now if you're doing it on a graphing calculator, it's a little bit different. This is still the same problem, but I want you to try it and make sure that you get the right answer, okay? So you push the 2, the display shows this. You push this little symbol, like the caret symbol, it's like that. And the display shows this, the 2 with the caret after it. And then you press 5, so it'll say 2 raised to the 5th power, and then hit enter, and you should have the number 32 if you did it. So definitely pause this and practice doing that problem, okay? Now, once you've got it down, we're going to jump into example 114.1, and you can see how it gets really complicated really quickly because they want us to do 1.06 raised to the 8th power using a calculator. I mean, if you were trying to figure it out, you would have to do 1.06 times 1.06 times, I should do x's so it's not confusing, times 1.06, and you do that 8 times. So you could do that, but obviously that is the long way, so you want to be able to do it on a calculator. So let's go through those steps again. If you have a scientific calculator, so turn your phone to the side, see if you've got all of these keys, okay? And again, the problem is, I'm going to write it down so I can see it, 1.06 raised to the 8th power. Okay, so we press 1 and then the point 1.06, and then you hit y to the x, and then 8 is the exponent, and then push equals. If you did it right, you should get this big long thing. And you can see that that makes sense because this number is barely over the number 1, and if you do 1 times 1 times 1 times 1, it's going to be pretty close to 1. But if you're adding a little bit more in there, or multiplying a little bit more, I should say, then you're going to get something that looks like this. So that does seem right for an answer. Now, let's also, don't skip this step, please don't skip this step. Also do it on your graphing calculator. Same problem, 1.06 raised to the 8th power. Okay, here we go. Type in 1.06. The display shows this. Then do your caret. The display shows that number with a caret after it. Press 8 and then enter, and it will give you the same answer. Cool. All right. We are done with that section, and we're going to move on to exponential growth. And I think it's pretty funny that the first example of exponential growth talks about breeding rabbits, because they do have a lot of babies. Okay, so here's the problem. Jimmy had 150 rabbits. If the number of rabbits doubled every year, he would have 300 rabbits at the end of the first year. Ignore that. Okay. He will have 300 rabbits after 1 year. So this is 1 year. Okay. Then he has 300. And at the end of 2 years, so this is maybe another year. So you go from 1 year to, well, I won't make it confusing. Let's put 2 years here. After 2 years, he's going to have 600. Okay. Cool. So it goes from 150 to 300 and then to 600. And this is an example of exponential growth. Okay, so let's take a look at this a little bit more closely. If you have R0, we're gonna use R0 to indicate the number of rabbits in the beginning. So R means rabbits. R after 0 time, because he started with 150, is going to be 150. And just look at this for now, 150 times 2 to the 0, and it'll make sense in a minute, but it probably won't make sense right now. Like, why are you multiplying it by 2 raised to the 0 power? And the answer is going to be because this 2 means what's the rate of growth? And it tells us that it doubles every year. And if it doubles every year, that means we're going to have to be multiplying by 2. Okay? But this first R0, that means no time has gone by at all. That's just the number of rabbits that he started with. So R0 is 150, and you want to keep it 150. And if you multiply it by 2 to the 0, what's anything raised to the 0 power? It's 1, right? So this is just a big 1. Big fat 1. 150 times 1 is just 150. So 150 when he starts out. Okay, now at the end of 1 year, so this is the number of rabbits after 1 year. It's going to double, so it's going to be 150 times 2. So this is now 150 times 2. Now, I'm just going to write 2 to the 1, and I know that's not going to make a ton of sense right now, but you'll see the pattern in a minute, okay? Now, after 2 years, how many rabbits does he have after 2 years? It's R to the 2, and what it is 150 doubled after 1 year, doubled again after 2 years. So 150 times 2 times 2 again. And you can simplify this, 150 times 2 times 2, by saying 150 times 2 raised to the 2 power. And that's where those exponents are coming from. This exponent means you doubled it twice. Okay, let's keep going, and because this really needs to stick in your brain. This is important. After 3 years, the number of rabbits doubles again. So you start with 150. After 1 year, you're doubled. After 2 years, you're doubled. After 3 years, you're doubled again. So it's 150 times 2 times 2 times 2. Now it makes sense that after 3 years, this is going to be 150 times 2 to the 3. Okay, so let's look at the pattern. This is the rate of how much it grows every year. They could have told you that it triples every year. And then this would have been 150 times 3 times 3 times 3. And then this number would be 3, right? And then this number, where do we get this number coming from? It's how many years has passed or how many times you've doubled it, depending on the growth. It might double every month or something like that, right? But this is the number of years in this example. And this is basically the rate that it's growing, okay? So the overall pattern after t years, so t is just a variable, it could be 5, 10, 15, right? Anything. The number of rabbits after t years is equal to 150, because this is what you started with, and you multiply it by 2 because it doubles every year, and then t is the number of years. So this formula is representing exponential growth. And it's exponential because you multiply it by something with an exponent. Now, if you were to graph the number of rabbits over the number of years, you would get a graph that looks like this. So this is the number of years. On the y-axis, we have the number of rabbits. Now, we didn't start with 0. We started with 150 rabbits. So that's why you start here with x at 0 years and y is 150. That's their starting point. And then after 2 years, it doubles to 300. It doubles to 600. It would double again to 1200 after 3 years, right? So this is the overall equation. And the shape of this curve, whenever you see that, this is exponential growth. This type of growth is called exponential growth. This is a good type of growth if you want to have a lot of rabbits or a lot of dollars or a lot of something like that. It could be bad if you have like the number of bacteria or tumor cells or something else bad growing that way. But in this example of exponential growth, we start out with the number of rabbits after t years. Then this is going to be the number of rabbits that we had originally. That's why we have an O here, original number of rabbits. This y, which in this case was 2 because it tells us that it doubles every year, is your growth multiplier. They could say it triples every year, it quadruples every year, whatever it is. And then this t is the time frame after t years in this example. Okay, so this, I want you to memorize this equation because we're going to use this equation every time there's exponential growth. So your original number multiplied by your growth multiplier, and don't forget the t, that's what tells you that it's exponential growth. You're raising it to an exponent. Okay? All right, one place where we use exponential equations a lot is at the bank, or is that in the financial market. And hopefully it's on your side, meaning that if it's on your side, your amount of money is multiplying. But it could also be that your amount of debt is multiplying, or the amount that you owe. That would be a bad thing if that grows exponentially. So here's an example. We're going to start talking about banking. So when you put your money in the bank is basically going to pay you to let the bank use your money. It does not mean that all the money that you put into a bank just goes into a vault in the back of the bank and it's just sitting there doing nothing. No, the bank is actually using your money and they're investing it, and they don't have a vault. They're taking that money and they're using it. And they have to give you something so that they, I guess, entice you to let them use your money, and that's called interest. So there's two key words that you need to know here. The first is principal. Principal is the amount of money that you put in the bank. Maybe you put in $100 in your bank account to open it up, right? And then the amount that the bank pays you, that's called the interest. So the principal is the amount of money that you put in. The interest is how much the bank pays you for using their bank. Now, you could deposit $100 into a bank account, and they might say, okay, we're going to give you 4% annual interest. That would be pretty good, actually, 4% annual interest. And what this means is that at the end of 1 year, 1 calendar year, so you have to wait all the way from January to December. If you put $100 in the bank and they're going to give you 4% annual interest, you're going to end up getting back $104. Okay, let me move this up. You're going to end up getting $104. Now, there's a way that you can write this, and this is using that exponential growth equation. So, let me make sure that you can see it. Like, this is usually, so it was RT before. Let's put in dollars. How much dollars would you have after a certain time frame? You would have the principal, or R0. Remember the R0 from the rabbit example? This would be the deposit that you made originally. So your original deposit, or the principal money. This is your growth multiplier. And it's not 4%, it's not 0.04. That would be wrong. It has to be 1.04 because you get to keep all the money that you put in. So if it was just a fraction of this, it would be 0.04, but you have to add in the money that you still have. That's why it's 1.04. And it's raised to the n power, and that is meaning after n number of years. After 1 year, you would have, after 1 year, let's erase this and put the number 1. After 1 year, you'd have $104, right? And you could also erase this and say, how much would you have after 2 years? So you do the exponents first. You would have to figure this out first, and then you multiply it by 100. Okay, in this example, the interest rate is compounded annually. And that means that they're only going to give you interest at the end of a calendar year. They're not going to do it every month. They're not going to do it every day. At the end of the calendar year, they will give you that amount of interest. So, in this example, we're going to do another equation that's very similar to the rabbit equation, okay? But it's going to be a little bit different because we're using different variables here. Let's pretend that R is the interest rate. Okay, so R is going to represent the interest rate that they tell you. This is your starting amount of money. Okay, that's going to go here. This is the amount that you have after T number of years. So A subset T. So this is just like that equation above. You have A subset T is the amount that you put in, maybe $100. And here is the interest rate. And remember, it was 1.04, not just 0.04. Because if you just put in R, or 0.04, that would actually be only a fraction of your money. You're figuring out something different. But if you want to figure out the total amount of money you have to add a 1, because this is your original what you started with, 1 times whatever you started with. It could be like $30 instead of 100. It doesn't have to be 100. But it's 1 plus the interest rate. Okay? It could be written as a function. So this is written as A subset T, your exponential equation. This one's written as a function. That works too. You could totally do it that way. It's like putting money into the machine. It spits out, you put in the X, it spits out a Y. That's a function, right? And then if you simplify this or kind of multiply it out, you end up with the same form as the rabbit equation. Okay, so this is an exponential equation because you've got after number of time, and the time goes here in the exponent. Your amount total after t number of years is your original amount multiplied by y. What is y? Y is this whole thing, 1 plus r. So let me just, y equals 1 plus r. This will make more sense when we do an example. But it's just plugging in like an x and a y into your exponential equation. And then, of course, don't forget the exponent, t number of years. So this is an exponential equation. Memorize the way that that looks. Okay, let's do an example. 114.2. The number of bacteria in the dish tripled every month. So here's a picture of bacteria, and they do grow exponentially if you put them like in a petri dish. Petri, you'll use that term in science, petri dish. Okay, so the number of bacteria are going to triple every month. You started out with 2,500 bacteria at first. How many bacteria are there going to be after 10 months? So remember that equation. The amount after a certain number of time is equal to your original amount times y, that's going to be your growth multiplier, times, or raised to the exponent of t. Okay, now just let's plug in what we know. Okay, so your original amount of bacteria were 2,500. Okay, now what's y going to be? It says that it triples every month. So for y, I'm going to put in 3. And how many months went by? Because that's the t, that's going to be the exponent. And it says after 10 months. And this is all going to be equal to the amount that you have after 10 months. So instead of AT, I'm going to write A10, A subset 10 after 10 months. So now, how do we figure out this problem? Well, we're going to start using our calculators. So this is 2,500 times 3 raised to the 10. So first, we have to figure out this part, 3 raised to the 10th power. So use your y to the x key, put in the number 3, then put in y to the x, then put in 1, 0. That's what it says on your display. And then when you hit equal, it turns into this. And you can see how exponential growth multiplies super rapidly. Okay, but that's not the answer. That's just the 3 raised to the 10. So we have to multiply. That means that each bacteria multiplied that much. So 2,500 times this answer that we got on the calculator, 59049. Multiply that out, and what are you going to get? You're going to get this big thing. So it's going to be 1.4762 times 10 to the 8th. What does that mean? That means that we can move this decimal point 8 times over, right? Okay, cool. Right? Mo money, mo problems. This next example is going to talk about exponential growth of money. Yes, this is what you really want to know. I mean, you want to be able to figure out these problems. Like if you make a mistake on how many bacteria are in the dish, kind of whatever, who cares? But if you are like Elon Musk or something, you got to be able to do this, right? Because you don't want someone stealing your money from you. Let's say James deposits $500 into the bank and the interest is 7% interest. Ooh, that's pretty good. I would totally take that. It's usually not that high. And it's compounded annually. How much money is he going to have after 14 years? He just leaves that money sitting there, doesn't add to it, just lets it get interest. After 14 years, how much money did he earn? Okay, so let's write the basic equation. Okay, the basic equation. Your amount after time t is going to be your original amount times your growth multiplier. Now, when we're talking about interest rates, the y, or your growth multiplier, is going to be 1 plus the interest rate times, or not times, raised to the exponent of t. Okay? Now, we just plug in what we know. The amount that he's going to have after 14 years is going to be the original amount, $500, times 1 plus 7%. 7 is going to be 0.07. All of that is raised to the exponent of 14. So I can simplify what's inside the parentheses first as just 1.07. Okay? So now this is the kind of problem that we have to do on our calculator. So let's take a look at how we do it. First, we do the exponent, order of operations, right? So we're going to put in 1.07. That's what it says on your display. Hit y to the x. It still says that. Hit 14 because it's 14 years. Then hit equals. You are going to get a number that looks like this, 2.578533415. Okay, but remember that's just this part of the equation. So we need to write 500 times that. Okay, and that's how we get $1,289.27. So that's how much he's going to have after 14 years. Now, they could also ask you, which they did ask you, 2 questions in this example. The first one was, how much money did he have after 14 years? And the second one was, how much interest did he earn? So how much interest did he earn? This is the total amount that he has after 14 years. So all you have to do to figure out how much interest he earned is to just subtract $500 from this. Because that's what he had originally. So to answer that second question, it's 789.27, only because we had to subtract the amount that he started with. He didn't earn that money from the bank in the form of interest. He invested that much money into the bank to start out with. All right, there is another section to this lesson, so wake up because we are still going strong. Now, this is using the graphing calculator to graph exponential functions. Yay, this is going to be so fun. Okay, there's lots of graphing calculators out there. The one I ordered for you is one that you can use. You are allowed to use it on the SAT, ACT, probably some of the tests that you're going to have in school. They're not going to let you have your phone, even though you could do things on a graphing calculator app. They're definitely not going to let you have your phone on any of these big exams because it's too easy to cheat. It's too easy to phone a friend and ask for help, right? So we're going to start practicing how to use a graphing calculator as a tool for graphing some of these functions. So let's start with an easy one. We're going to graph this using your graphing calculator. This is a function, kind of like f of x is equal to 2 raised to the exponent x, right? This is kind of a function. So we're going to first enter the function into the calculator, okay? And it might look like this. When you enter it in, it might look like this. F of x, function 1, is 2 raised to the x. This is what the caret means. It's raised to the exponent x. So you're going to have to play with your calculator a little bit and figure out how it's done. Now, once you put in this function or this equation into your calculator, the graphing calculator could graph anything because x and y, you didn't define the domain yet, right? This could be negative infinity. You don't want it to be working forever on that. So you have to pick a range. Now, we're going to let x vary. Okay, next step, define range. Maybe, here's a good example that they want you to do. Maybe x goes from -5 to +5. And that's just kind of randomly picked by this book. And then, so -5 to +5 is just a reasonable range. I don't know. Then you have to select y values that are going to let you see as much of this graph as possible, right? Because you don't want to be too zoomed in on the up or down axis or too zoomed out. If you're too zoomed in, you might just see like a portion of this line and not know what the shape is. If you're too zoomed out, it might look like a straight line, right? So you want to have the right range as far as x and y, and also the right range as far as y. Now, if you just pick randomly x from -5 to 5, then you don't want to pick the y randomly because it's too random. So what you're going to do is you're going to plug in -5 for this x, and then you're going to plug in +5 for this x, and you're going to get two numbers for y when you calculate that out. That gives you a reasonable range. So if we put in the number, let's see, okay, here's our function. Again, I'm going to put y is equal to 2 raised to the x. If you put in -5 for that x, I'm going to erase this. I'm going to write -5. What do you get? Now you can just plug that into your calculator, and what you'll get is, what? 2 raised to the -5? Oh, you get 1/32. Why do you get that? Because 2 raised to the -5 is the same as 1/2 to the 5th, and then 2 to the 5th is 32. We already figured that one out. So if x is -5, y would be 1/32. So this is the -5 part of the x range. If the x is that, y is going to be that. Okay, what if x is +5? Well, it's just y is equal to 2 raised to the 5th power, and then that's just 2 raised to the 5th power is 32. So if you pick a range for x that goes from -5 to +5, then your range for y is going to be 1/32 all the way up to 32. Now, this doesn't really make sense to put that in for a y, but it's kind of close to 0. So we're just going to pick 0 for the y, and 32, this is the range. So if you put that in and then graph it, you should get a graph that looks like this. See, exponential growth on a graphing calculator. And then what's cool about it is that you could be like, after 1 year, it's something like that, 2 years, 3 years, this is the x-axis, this is the y, and you can play with it and see what you get for different things. So cool. Make sure that you pause this video and try this on your graphing calculator. Okay, last example, and then this lesson is over. I know this is a long one. Hang in there. Hang in there. Okay, yes. We're going to do example 114.4. Use the graphing calculator to graph this function. Okay, so we're going to do y is equal to 1/2 raised to the x. Again, this is another exponential equation because you've got an exponent. And you could also make it look like this. Instead of using 1/2, just use the decimal point, 0.5. So you're going to put this in your display, or you're going to put this in your display depending on what you're using, okay? Now, we have to put in a domain or a range. So again, for x, let's just randomly pick -5 to +5, okay? And then what would we put in for a range for y? Well, let's plug in a -5 to that equation. Okay, so y is equal to 0.5 raised to the -5. That's the same as 1/0.5 raised to the 5th power. And what would we get for that? We would get, we would get, let's see, we would get 32. 32. Yeah, 32 for that one. And then if we put in positive 5 for the top end of our range, it's going to be, the top end of our range is going to be y is equal to 0.5, this time raised to the 5th power, and you get 1 over 32. It seems weird. It's the opposite of the previous example, but it's only because this is a fraction. Because I was confused for a second. Why would we get 32 and 1 over 32 this way? But it's because this is a fraction, so you're exponentially multiplying a fraction, so you get an exponentially big, or smaller, I should say, fraction. Okay, and you can tell it's going to get smaller the more positive x is, because when you graph it, it looks like this. It's like a negative exponent, exponential growth. So cool. Like the more negative you get, the more exponentially it grows. Yeah, cool. All right, so make sure that you can plug it into a graphing calculator and get something that looks like that. And then you're going to practice with your practice problems and then do your problem set, okay? Good job. You finished this lesson. Love it. Okay, bye, Zach. Have a great day. Bye.